in my talk. So I'm Yulong. So last year, the same time, I'm in Berkeley, advised by Professor Yulong and Professor Berkeley. And this year, I graduated and I joined the industry research scientist position, but still in the Bay Area. So switch from 5 minutes driving to 1 hour drive. So that is why I'm here in the afternoon session. And my talk today is about the market-level version of quantum signal processing, so we can use to solve scientific computing problem very efficiently. And we have some, this talk is based on 2 papers. I attached a QR code here, and there's also a personal website myself. So as we know, quantum computing is originated from the proposal by Richard Feynman, saying that we can solve nature by using the power of nature. Because there are a lot of complex physical chemical systems that are very hard to be simulated, but we may leverage the power from nature to simulate this system by itself. And by moving to the quantum realm, we may switch from Feynman to a superposition. And after a few decades, we didn't get the superposition of Feynman, we get superposition of a lot of quantum computers. So a natural question for us is whether we can use the quantum computer to do something that is useful. One thing we can consider is the ground state preparation problem. So assume we have a Hamiltonian H. We have the spectrum decomposition. We get the lowest eigen value and eigenvector beside 0. That is the ground state of our Hamiltonian, and we get all the excited state. And the goal for us is to query the information of the Hamiltonian, but to extract the information of the ground state of this Hamiltonian. And this problem is very important because we can use it to simulate, to study the physical and chemical properties of some systems to facilitate the discovery of new materials. And it can also be useful to do quantum metrology, because for some quantum gates, we're able to use this ground state preparation problem to learn the Hamiltonian property inside the logical quantum gates. It's also useful to solve linear system problem that is the foundation of applied mathematics, and it's also a core interest for almost everyone in the computing. So in order to query the information on the Hamiltonian, there are a lot of different ways to do that. So one thing I want to mention today is the so-called Hamiltonian evolution. So we can query the information on the Hamiltonian by leverage the time evolution of the Hamiltonian. So we have the H, we're able to evolve the system according to some time, according to this Hamiltonian, to harness the dynamics of the Hamiltonian to insert some information into the system. And time evolution is very useful because a lot of physical and chemical Hamiltonians can be easily simulated on the quantum computer, for example, using totalization or using some other efficient quantum algorithms. And not only for the ease of simulation, it can also be simulated efficiently. That is a property called fast forwarding. So we may simulate the Hamiltonian with a cost that is sublinear in the time t. So let's imagine, suppose we have a TFIM as Berkeley ice model without the transverse field, then we can directly use some access to the YYZZ gates to synthesize our time evolution of Hamiltonian. So that can be easily implemented, and the overall cost is sublinear in the time t. And for some very ideal systems, for some very ideal spin system, we can also do something that is even better. We can simulate the Hamiltonian with a cost that's almost independent of time t by using something like Gibbons rotation. That follows a series work by Rolando Solma. And this motivates us to think about how to design a quantum algorithm by querying this time evolution of the Hamiltonian with respect to some time t. And among this game, there are a lot of strong players, and most of them can categorize into 3 different aspects. One is for linear combination unitaries. So that is proposed by Charles Kosari and Soma in 2017. It's basically a way to combine some unitary fragments into something that can implement a functional circuits. And the second part is very classical. It's called quantum phase estimation, or QPE. So it's discovered 30 years ago, but recently in a paper by Google for topological data analysis, they integrate a method called resource state to enhance the efficiency of this QPE method so that it can also be state of the art. And the next one is called quantum signal processing. It's my favorite because it's a topic of my dissertation. And it's a way for us to use the very complex circuit structure to do the quantum algorithm by integrating the localized rotation and some system-wise Hamiltonian evolution in the system. We can zoom into some details of the signal processing. So in the classical world, when we talk about signal processing, we may have some signal that can be a sound wave, can be a light wave or electromagnetic wave, but everything can be described in terms of some kind of wave. And we can do the Fourier transformation, we can analyze spectrum. And the quantum world, we also have something called quantum signal processing. So we have some tunable rotations, that is something acts locally. And we also have a Hamiltonian evolution that acts like a logical Z rotation. We have an X rotation and Z rotation. We can interleave this sequence to get an interleaved output signal that is X rotation, Z rotation, X rotation, Z rotation. So that is a very good analogy to the classical EM wave. Because we have a rotation in two orthogonal directions, we're able to get something carrying the information by get the output EM wave. So if we look at this interleaved sequence, we look at just one repetition, a blue grid and an orange grid, we're able to get a pulse, a bump like this. But if we are able to leverage this sequence for 3 different times, we're able to implement something with a flat top. And if we are able to interleave this sequence for n different times, then we can, in theory, we are able to get something like a sigmoid. So once you want to do some machine learning research in the future, maybe you can use quantum signal processing to design your own activation function. And this is guaranteed by the theory proposed in the 2 papers, Low and Chuang and Yulong, Su, Low, and Wade. So they prove that this is guaranteed quantum signal processing can implement a universal function transformation of any Hamiltonian. That gives us a lot of room to design quantum algorithm because we are able to just transform our Hamiltonian to be something of our target. For example, if we want to do ground state preparation, we just transform the Hamiltonian to be the projection onto its ground state sector, and then you solve our problem. You want to solve the linear system problem, you transform the Hamiltonian to the inverse of this Hamiltonian, so that you can invert the linear system by directly invert the Hamiltonian. And back to the ground state preparation problem, suppose we are able to transform the Hamiltonian according to some function, then we can still leverage the spectrum decomposition to see that we only want to keep the component of the ground state, but kill all of these excited state components. And in terms of the mathematical formalism, we can write it as a ground state preparation. We get a G function that's almost equal to 1. For the transition gap, we don't care because there's no components lying in this gap. But for the excited state, we want to enforce it to be almost 0. So in terms of spectrum, we see that we want to keep the ground state component by killing all this excited state component and with whatever transition happens in this delta gap. And this can be implemented by using our interleaved structure because we have X rotation, X locally, and we have a Hamiltonian evolution be controlled to affect the overall system. Then we have an X rotation, and we have a logical Z rotation and Hamiltonian evolution, so on and so forth. By using this sequence, we're able to get the ground state, and the detailed receipts can be found in our paper. But by analyzing this property, we have to have a one guarantee, that is the evolution time t. Because our Hamiltonian can have a very large spectrum. And when we talk about time evolution, it's more like a complex exponential. There's a multi-branch function. The Hamiltonian eigenvalue can loop around the unit circle. So in order to make all this eigenvalue uniquely determined on the unit circle, you have to do the normalization. That means you have to determine this time to be something that is almost 1 over the norm of h, so that your Hamiltonian is bounded by norm 1, and you can uniquely determine all these eigenvalues on the unit circle. But this rescaling gives us something that is not desirable, because we get the degree of our approximation polynomial, like this one, scale as linearly in our Hamiltonian norm h. The reason is because once you scale down Hamiltonian, the transition gap becomes smaller, and then it's very hard for you to accommodate this sharp transition, and consequently you get this linear scaling in terms of Hamiltonian norm. But that is not the case in other methods, because the secret groupon for LCU and QPE is a so-called select oracle. So if we open the textbook version of QPE, you may find some circuit structure like this. You get the unit rate applied for many times until you get the unit rate applied for just single time. And this is called select oracle because you have hierarchical structure, Hamiltonian evolution at variable time scales. You just evolve the system with a unit time one, and then you evolve it with time two until two to the p minus one. You get a sequence like O of h of time that is our time step 1 over h, then you get 2 over h, 4 over h, so on and so forth. And this will give you a sequence that is very hierarchical. And that makes the exponential reduction in the query complexity because assume that our Hamiltonian can be efficiently simulated without any cost depends on time t. Then you directly have a kind of binary search structure here, and you get a logarithmic dependency in the Hamiltonian norm h. That is something that is very interesting because we have an LCU and QPE that was the algorithm discovered before QSP, but QSP is similarly less efficient compared in this specific example. And that motivated us to ask a very interesting question: how can we make this QSP method stronger? And it can be broken down into two different sub-questions. The first one is whether we can understand the exponential separation in terms of this specific example. And second one is whether we can bridge this gap by making the QSP method stronger. We can take some inspiration from classical numerical analysis. So if we open the classical numerical analysis textbook, something very important and very common in the midterm or final exam could be composite integration rule. So we have a rule that is trapezoid rule, but we can make it very complex by halving the step size of our integration scheme. And then we may find that until some step size, we are able to recover the integral with efficient, with a sufficient precision. And that means to achieve the target precision, a reasonably okay step size should be fine instead of just use a step size that's almost machine absolute. And back to our problem, we see that QSP have a fixed step size that's almost 1 over h. But for the LCU select oracle, we have a variable time scale that's 1 over h, 2 over h until something over h. And that means that we are able to leverage a very hierarchical structure to find the reasonable okay step size in the LCU formalism. But we have a super accurate step size in the QSP formalism. And that makes us to conceptualize our research question as whether we can propose a multi-level structure of the QSP method so that we can accommodate this variable timescale in our quantum algorithm. And we know that the issue is our Hamiltonian have a very large spectrum radius, and we want to make it smaller. So we may able to first halve the spectrum radius by using some cheap filter so that you can make this Hamiltonian become smaller and then proceed to the next step. So let's take a look at this filter function here. So if you have a degree that is equal to 10, you almost recover the trend of this function. Once you make your degree of the polynomial become larger, like 50, you almost recover this flat top here, and the transition among the gap. So that is a very cheap filter for us to implement on near-term or near-future quantum computers so that we can halve the spectrum radius of the Hamiltonian. And finally, we do this iteratively. We're able to get effective Hamiltonian with a super small spectrum radius that can be accommodated into our original formula. Let's look at this scheme. So we have a Hamiltonian original with a large spectrum radius. Then we pass it to this filter. We get a Hamiltonian with this spectrum radius that is half. And then we apply it many times. Sequentially, we get output that is almost with the almost constant rate spectrum radius in terms of the Hamiltonian spectrum. And we can also look at this flow chart. So originally we have a distribution of supported on different ground state or excited states. Once we apply the first level of filter, we just half our spectral radius by killing some excited state components. And then we apply the second filter, we make the spectrum radius even smaller. And then we proceed to the next step. We kill more excited state to get a smaller effective Hamiltonian. And for the next step, we get effective Hamiltonian with almost just 2 eigenvalues. And then for the last step, we just kill the only first excited state to get the ground state of Hamiltonian. So that is the multi-level version of the quantum signal processing, so that we leverage this, the eigenvalue, the time evolution of different time scales to kill the eigenvalue, to kill the excited state components in our system. And all of this requires only logarithmic dependency in the spectrum norm in order to make our Hamiltonian spectrum radius small. And each card a cheap filter that scale as log1 or epsilon dependency in terms of polynomial degree. And the time step is also hierarchical. We get 1 or h, 2 or h, until 1 or delta that keeps our spectrum radius contains only one eigenvector, that is a ground state. And in terms of the filter design, we can conceptualize our protocol as a function composition problem. So we have a first level filter that is something worth that. And then we get a sharper filter. We get, for the level 3, we get a filter, but we get a leakage in the excited state. But it's okay, because in the previous level, we kill all of the excited state components. And then we get a composition, we get this very sharp filter like this. And the quantum signal, this model-level quantum signal processing circuit is also very compact, because we are able to use something called compression gadget to track all the successful filtering at different levels. And this will give us a very concrete and coherent circuit implementation. And finally, we can discuss the complexity improvement by using the model-level quantum signal processing. So the gate complexity, we get a logarithmic dependency in the Hamiltonian spectrum. That is comparable with the LCU slack oracle, and is an exponential improvement compared with the original QSP formula. But for the LCU, we have a slack oracle, but we also have some state preparation for propel oracle. It's very expensive. And in terms of the ancilla qubit dependency, we get an exponential improvement against the LCU's ancilla qubit count, because we use a compression gadget to get a compact representation of the quantum circuit. We get a log-log dependency instead of log dependency. And that is almost everything I have discussed for this table. And everything can be found in our paper. And we also listed the comparison with the QPE in our latest version, which will be released later. And we also get a quadratic speedup compared with the LCU slack oracle, because we don't have something called one norm scaling, which you can find details in this reference 1. And for the compression outlook for my talk today, so we discuss the philosophy of our multi-level quantum signal processing method by integrating the power of QSP, compact circuit representation, and LCU's powerful select oracle to get a scheme that can solve the ground state preparation with a greatly improved gate complexity and exponentially improved ancilla complexity. And it also breaks the gap between QSP and LCU in terms of the ground state preparation problem with fast-forwarding Hamiltonian evolutions, which can be realized in many physical and chemical systems. And our method can also be used to study the low energy physics by just applying an early stop criteria, because you can just shrink the effective Hamiltonian radius. And once you attain some low energy sector, you just stop it and you pass this effective Hamiltonian to be some other quantum subroutine for the analysis. And you can also derive effective Hamiltonian with a reduced spectrum, and it can be applied to other algorithms because it's a coherent procedure. And it also provides new insight in quantum engineering, because the heart of this method, it lies in the decomposition of some filter function in a multi-level version. So it's a kind of connection, or it's a kind of application quantum algorithm viewpoint into the quantum engineering. And thanks for the attendance. And this is a joint work between myself, Professor Yulong, who is my current lab mate in Lin's lab, and he's currently a professor in Duke Mathematics, and also with Professor Ling. There's 2 references I mentioned today. And as a common practice of my talk in this 4th semester, I will always put QR code here saying that I'm on the academic job market this year. So if you have any opportunity, feel free to reach out. Thanks.
Yeah, so the circuit structure looks very similar to the time marching differential equation solver. So
Yeah.
do you need to apply some sort of uniform singular value amplification over here, or is that kind of taken care of?
Yeah, thanks. That is a very good question. The circuit looks like time markings because we both use this compression gadget to track this successful of something with exponential improvement. But the question the difference here is we don't use this we don't use the uniform singular value amplification here because we don't have the decay in the norm. That is a problem in the previous method. In the work you mentioned. But in our case here, we only need to filter it in some different steps. So there's no issue of the decay of success probability.